Now let us see how to solve a recurrence equation using forward and backward substitution. Let us take the example of tower of Hanoi, where m of 1 equal to 1 and m of n equal to 2m of n minus 1 plus 1 for n greater than 1. Let us mark these equations as 1 and 2. Following forward substitution, we already know that m of 1 is equal to 1 and m of n, that is 2, which is greater than 1, we follow the equation number 2. Therefore, substituting n equal to 2 in equation number 2, we get 2m of 2 minus 1 plus 1, which leads to 2m of 1 plus 1. We know that m of 1 is 1. Substituting, we get 2 into 1 plus 1, which is 3. Similarly, for m of 3, we substitute n as 3. 2m into 3 minus 1 plus 1 gives you 2m of 2 plus 1. We know that m of 2 is 3, which gives you 7. Similarly, the general equation is m of n, which is 2 to the power n minus 1. Let us see how to solve the same equation using backward substitution. We have m of 1 equal to 1 and m of n equal to 2m of n minus 1 plus 1. We mark these two equations as 1 and 2. In order to find what is m of n minus 1, we substitute n minus 1 in equation number 2. Therefore, we get 2m of n minus 2 plus 1. We substitute this in the second equation, m of n. We arrive at 4m of n minus 2 plus 3. In order to find what is m of n minus 2, we again substitute m of n minus 2 in equation number 2. So, m of n minus 2 equal to 2m of n minus 3 plus 1. We substitute this in equation 3. Therefore, m of n is equal to 8m of n minus 3 plus 7. This is 4. Equation number 4. In general term, we write m of n is equal to 2 to the power I m of n minus I plus 2 to the power I minus 1. So, what is n minus I equals to? We have m of 1 is equal to 1. So, in order to make this as 1, we equate n minus I equal to 1. So, I equal to n minus 1. Substitute I equal to n minus 1 in equation A. So, m of n is equal to 2n minus 1 m n minus 1 plus 2n minus 1 minus 1. Start. I repeat the equation number B. m of n is equal to 2n minus 1 m n minus n plus 1 plus 2 to the power n minus 1 minus 1. Therefore, 2n to the power minus 1 m of 1 plus 2 to the power n minus 1 minus 1. We arrive at 2n minus 1 plus 2n minus 1 minus 1. 2 into 2n minus 1 minus 1, which is nothing but 2 into 2n minus 1, 2 into 2 to the power n divided by 2 minus 1. Both the 2's get cancelled. Therefore, 2 to the power n minus 1 is the recurrence equation of tower.
We will see how to solve a recurrence equation using smoothness rule. We use smoothness rule for an equation involving n by I term. So, consider this equation where x of n is equal to x of n by 3 plus 1. So, using smoothness rule, we assume n is equal to 3 power k. So, the general equation becomes x of 3 power k is equal to x into 3 power k by 3 plus 1. So, this becomes x of 3 power k is equal to x of 3 to the power k minus 1 plus 1. Keep this as equation 1. Now, find for x of 3 to the power k minus 1. Substitute this in equation 1 to find it. So, this becomes x of 3 to the power k minus 1 is equal to x of 3 to the power k minus 2 plus 1. So, substitute this in equation 1. So, this becomes x of 3 to the power k is equal to x of 3 to the power k minus 2 plus. So, this becomes equation A. So, now we find for x of 3k minus 2. So, 3 to the power k minus 2 we substitute in equation 1. So, it becomes x to the power 3k 3. So, x of 3. So, this is x into 3 power k minus 3 plus 1. Substitute this in equation A. So, this becomes x of 3 power k is equal to x of 3 power k minus 3 plus 1 in plus 2. So this is x into 3 power k is equal to x of 3 power k minus 3 plus 3. This in general we write x of 3 power k is equal to x of 3 power k minus I plus I. In order to find x of 1, since x of 1 is equal to 1, we assume I is equal to k. So x of 3 power k is equal to x of 3 power k minus k plus k. So this is x of 3 power 0, which is x of 1 plus k. Since x of 1 is equal to 1, it's equal to 1 power 1 plus k. In the beginning, we have assumed n is equal to 3 power k. So this becomes x of n is equal to 1 plus log of 3n.
We are going to see how to solve a linear homogeneous equation. Linear homogeneous equation cannot be solved using a forward substitution or backward substitution method. To solve such type of equations, we use the following method. For example, let us take the recurrence equation of Fibonacci series, which can be represented as f of n is equal to f of n minus 1 plus f of n minus 2. We can rewrite the equation as f of n minus f of n minus 1 minus f of n minus 2 is equal to 0, which is of the form ax square plus bx plus c is equal to 0, where a is equal to plus 1, b is equal to minus 1 and c is equal to minus 1. This equation can be represented as x square minus x minus 1 is equal to 0. Now, to find the roots of the equation, we have two rules. If the roots are real and distinct, then the recurrence equation can be represented as f of n is equal to alpha r1 to the power n plus beta r2 to the power n with initial conditions. If the roots are the same, then the recurrence equation can be represented as f of n is equal to alpha r power n plus beta n r power n. To find the roots, r squared minus r minus 1 is equal to 0, where a is equal to plus 1, b is equal to minus 1 and c is equal to minus 1. We use the formula r is equal to minus b plus or minus b square minus 4ac the whole root by 2a, where you get 1 plus or minus under root of 1 plus 4 by 2 into 1, which gives 1 plus or minus under root of 5 by 2, where the roots r1 is equal to 1 plus root 5 by 2 and r2 is equal to 1 minus root 5 by 2. Applying rule 1, we get f of n is equal to alpha plus root 5 by 2 to the power n plus beta 1 minus 5 root 5 by 2 to the power n. Now, to find alpha and beta, apply n is equal to 0, where alpha plus beta is equal to 0. Let this be the equation 1. Now, apply n is equal to 1, where f of 1 is equal to 1 and alpha into 1 plus root 5 by 2 plus beta into 1 minus root 5 by 2 is equal to 1. Let this be equation number 2. Now solve equation 1 and equation 2 to find alpha and beta. Let alpha be minus of beta. Apply alpha is equal to minus beta in equation number 2. You get minus of beta into 1 plus root 5 by 2 plus beta into 1 minus root 5 by 2 is equal to 1. Beta into minus 1 minus root 5 plus 1 minus root 5 by 2 is equal to 1, where beta into minus 2 root 5 by 2 is equal to 1. And now you find beta is equal to minus 1 by root 5. Substitute beta in equation 1. So alpha is equal to 1 by root 5. F of n is equal to 1 by root 5 into 1 plus root 5 by 2 the whole power n plus minus of 1 by root 5 into 1 minus root 5 by 2 the whole power n. Taking 1 by root 5 as common, you get 1 plus root 5 by 2 the whole power n minus 1 minus root 5 by 2 the whole power n. Therefore, f of n becomes 1 by root 5 into 1 plus root 5 by 2 to the power n minus 1 minus root 5 by 2 the whole power n.